which many of you do, and then the relay feedback experiment, which some of you will do. And let me see, how are we going to decide who does the alternate method?
Just not the alternate. Nobody does the alternate.
No. Was the alternate method easier or harder than the other method? Well, this one's easy. Okay, the people who already did it, get this one. It's very quick and easy. Frequency response. Let's talk about that first. The non-alternate people do the frequency response. It says bribery in that. Frequency response. We're going to observe the output function when you put a sine wave in. So the input is going to be a sine wave, and the output is also going to be a sine wave. However, they have different amplitudes. You see that right off. But you knew they'd have different amplitude because they have different units. One's percent and one's either volts or pressure or temperature or something like that. So you know the amplitudes are different. And we're going to measure the ratio of the amplitudes between the output over the input. Amplitude of the output over the amplitude of the input. Have you seen something before that was output over input? Gain is output over input, so it's the same ratio, same units as gain. Amplitude of the output, which might be units of volts, amplitude of the input, which have units of percent, so the ratio of the output over the amplitude. The ratio of the amplitude of the input over the amplitude of the output is called the amplitude ratio. Is that amazing? It just drops out, just like that. And we have an abbreviation for the amplitude ratio. John, you got any idea what the abbreviation for the amplitude ratio might be?
No, I wasn't thinking.
AR?
AR! You're good. Sweet. So we're going to call it the AR. Amplitude ratio, both capital letters. Amplitude ratio. Now, look at this. Let's see if we can measure where the peak is. The peak is right there. It looks like it's about 1 second. I'll tell you what, we can do this. The peak is right up here. And the whole 1 cycle is 5 seconds, it looks like. So I guess that's 1 1/4 seconds is the peak right here. Then we look over here. This peak, oh my, we can't compare these very well because they're different axes. That's 0 to 30 and this is 0 to 25. Other than that, this peak, let's see, 25, 1, 2, 3, 4. So this is 2.5. So this is close to 2. The peak occurs at 2 seconds rather than what was the other one? 1 1/4. So there's a shift between where the peaks occur. We call that the phase shift. The phase of this is following the phase of that. So we call that a negative phase shift. So, let's go down a little bit. Figure 6, all that, typical output. What frequency do you use for the sine wave input? I want you to do it for maybe as many as 10 different frequencies. So how do you choose a frequency? Well, one place to start is about a frequency omega. Omega is in, let me see, what are the units of omega? Omega are radians per unit time. radians per second, most of you radians per minute maybe. So we're gonna start at 1 over tau, tau for your system. Everybody know what the tau for their system is? The time constant? You know, yeah? Okay. You know what your tau is? Who needs to know their tau? Well, some of you haven't even done the experiments on the system that I'm switching you to, so you'll need to know the tau, so ask me about that in just a little bit. Okay. So tau. Which tau do you use? We saw today that some people had one tau based on the experiments and another tau based on the modeling. Which one do you use? I don't care. Whichever tau you want to use it. So, in fact, all three of you can use a different tau if you want to. So everybody write down what their tau is or make up a number. You can confer with your teammates if you want to.
All right, so ship sail, then I get on.
Huh?
What?
I don't know.
Good question, good question.
Write down.
The students who have a new system want to know what the tau for their system is, so let's do this. How do I get a new page up here?
You see like this in your lab menu, click on that tab.
Left,
Left. Yeah.
a little farther right.
Oh, there you go, there it is. I knew that. I know this is somewhere here. This time was scheduled. Oh, I know where it is. I know where it is. Let's take ivory for an example. Would that be okay if I use ivory for an example? If I say, yeah, sure.
Yeah, sure.
Well, you click on the absorber airflow station information. You click on the station information, and there is a model that tells you what K tau and KT naught tau are. What's that?
2.
2? So that's for a step up. I don't know what it is for a step down. Click on this one. It's still 2. If you want to see the SSOC, you're going to love this. There's the SSOC. Fascinating, isn't it? All right, so let's say it's for ivory and lavender, it's 2. We go over here to orchid. It's 5. Units are second. And teal will be the same thing. The step down is 7. So somewhere between 5 and 7. Use that whatever you want. Oh, there's your SSOC for, isn't that cool? What do you say about that, Ollie? Huh? Pretty sweet. Let's go back to here. So now, everybody take the reciprocal of that tau. You can use a calculator if you want to. Now that'll be the units of radians. How many of you really like radians? 1? 1 sometimes. How many like radians all the time? How many would rather use frequency in cycles per unit time rather than radians? You would, Philip? Okay. Who else would? Who else? You want cycles, so you have to divide the number of radians by 2 pi. So you now have omega. Divide that by 2 pi. What you got, David Dodd? Huh? What you got, Chris? Caroline? Negative?
You said take the reciprocal?
Yeah. Take the reciprocal of tau.
He wants to keep
I was like, wait a minute, yeah, just 0.08.
What'd you say?
He wants to keep the pi or put it in like it doesn't.
Wait,
Say it again.
yeah.
Keep the pi or put it in decimal.
Decimal form. I'm going to number. 1.6. Excellent. John has 1.6. Who has another value for frequency? Yes? 0.009. Huh?
0.79.
0.79. All right. Who else? You have one yet, Caroline? Ben? 0.199. Okay. Now then, I'm going to ask you to round that to one significant figure. No more than one significant figure. And use that as your initial frequency. There is nothing to be gained in using more than one significant figure in this experiment. For frequency. You with me? With me, Ronnie? Huh? So what's yours now? Did you give me one? Nick, you gave me one, John. What is it now? Oh, I love it. Did you give me one, Caroline?
0.8.
0.8, I love it. Somebody over here gave me one. 0.1. Excellent. Now then, you're going to do some experiments at lower frequency by approximately halving the frequency each time, and again, rounding to one significant digit. And then you might want higher frequencies where you double it, the frequency each experiment, and again, round it to one significant figure. And then how long should the experiment run? It has to run at least one cycle. So if you have a frequency of 1 cycle per second, it has to run 1 second at least. Except for the fact that it has to run long enough for your transient response to die out. So you know how long that is. It's around 6 times whatever your tau is. And then it would be nice after it steadies out, gets over the initial transients, if it runs it 3 more cycles. The reason we can like for it to have 3 good cycles is you can measure the amplitude ratio at each of 3 different places and use students T to find out what the variability in that is, and the phase shift at 3 different places, and use students T to figure out what the uncertainty in that is. Would you like me to run an example? Want me to run an example for you?
Yeah.
Who said pretty sweet? Did you say that, Ollie? Ollie's always interesting. All right, so let's run one. Oh, I know where to go. Refresh right here. All right. Notice these things change their name from what they were. This used to be voltage, this used to be speed, and now it says absorber airflow, parentheses, voltage, and this one says absorber water flow, parentheses. Let me run flow. Flow seems like an interesting one. You have flow back there, right? Huh? What's your initial frequency?
0.2.
I'm going to run sine. Your initial frequency? 0.2. And which region of the operating range are you using? What's the lowest percent and the highest percent of your SSOC?